Good day everyone. In today's video, we are going to consider a brief introduction to organic chemistry. In the past, compounds are divided based on their sources. We have inorganic compounds and organic compounds. Inorganic compounds are compounds obtained from non-living sources, from non-living things. Examples are the table salt that we eat at home, that's sodium chloride, calcium sulfate, sodium trisulfide, to mention a few. While organic compounds are compounds that are obtained from living things, from plants and animals. Examples are carbohydrates that can be obtained from plants, proteins that can be obtained from animals. In 1806, a physician by trade known as Jacob Berzelius came up with the definition of organic chemistry. He said organic chemistry is the study of compounds derived from biological sources, that is, plants and animals. And he came up with a theory known as vital force theory. He said vital force is a mysterious force that can only be found in organic material. They only exist in living things, in plants and animals, and that this vital force is actually needed to facilitate the synthesis of organic compounds, and that is why organic compounds cannot be manufactured in the laboratories. They can only be synthesized by plants and animals. In 1928, a German chemist, Friedrich Wohler, a doctoral student of Jacob Berzelius, that proposed the vital force theory, accidentally manufactured a biological compound known as urea. How did he go about this? He was attempting to manufacture ammonium cyanide by reacting an ammonium salt, we have it here, NH4 plus, and a cyanide salt. And instead of him getting ammonium cyanide, he ended up getting urea. And urea is an organic compound. This is urea. Let me break down urea for you. When human beings, when we take protein, it digests in our body. It breaks down into amino acids. Excess of amino acids cannot be stored in our body. Hence, they are converted by a process known as deamination into an harmless substance called urea. Urea is one of the components of urine. So therefore, urea can only be synthesized by human beings. So it is a big shock in the scientific community that urea can be manufactured in the laboratory. In fact, to clear his doubt, he decided to heat ammonium cyanide directly, and he ended up having urea again. So looking at it critically, he decided to discuss with his supervisor, and that is Jacob Berzelius. Well, they came up with an idea that if you look at ammonium cyanide, the molecular formula of ammonium cyanide is N2 H4CO. And if you look at urea too, the molecular formula of urea, that is also N2H4CO. Well, one is an inorganic compound, which is the ammonium cyanide, and urea is an organic compound. Molecularly, they are the same, but structurally, they are different. Maybe that is an exception to the vital force theory. Well, it still doesn't change the fact that the vital force theory should be debunked, and it has been negated because urea is manufactured in the laboratory. In 1845, another devastating blow hit vital force theory. Acetic acid, an organic compound, which according to vital force theory can only be synthesized in living things, was manufactured by Hermann Kolb in the laboratory. The straw that broke the camel's back was when Berthelot manufactured another organic compound, methane, in the laboratory. The synthesis of urea, acetic acid, and methane negated the vital force theory and birthed the modern definition of organic chemistry, which is the study of carbon compounds except oxides of carbon, carbides, carbonates, bicarbonates, etc., which are better considered in inorganic chemistry. Organic compounds contains carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, halogens, metals, etc. Basically, they contain carbon. All organic compounds contain carbon. Atomic number 6, the configuration is 2, 4. So it has 4 valence electrons. Okay, let's take a look at the SPDF configuration as 1s2, 2s2, 2p2. For the orbital notation, that's going to be, we have 2 electrons here following the Pauling exclusion principle, 2 electrons here, and following Hund's rule of maximum multiplicity, we are going to have 2 electrons here. So we are going to focus on the valence electron. We have 4 valence electrons. So out of these 4 valence electrons, carbon atom has 1 lone pair and 2 unpaired electrons. So we can say this is the ground state configuration of carbon. And considering its Lewis dot structure, we are having a lone pair here, is the lone pair, and this is the unpaired electrons. Now, carbon atom can actually gain energy, and when it does, the empty orbital in the 2s sublevel is filled with electron. Now, this is the empty orbital. Look at this blue tick here. Okay, that's the empty orbital in the 2p sublevel. So when carbon atom gains energy, electrons can actually move from the 2s sublevel to the 2p sublevel to fill up that vacant orbital. And let's see how that happens. Let's see what the configuration becomes. It's going to become 1s2, we have 2s1, and we have 2p3. For the orbital notation, we have 2 electrons here, we're going to have 1 here, and we're going to have 3 electrons here. Following Hund's rule of maximum multiplicity, electron goes in singly first into degenerate orbitals before pairing commences. So this is still the 4 valence electron. Now in the excited state configuration, carbon atom has 4 unpaired electrons, and using the Lewis dot structure, we are going to have this, and this is the first unpaired electron, the second unpaired electron, the third unpaired electron, the fourth unpaired electron. So these unpaired electrons can be used for covalent bonding. So surrounding carbon atoms, we have 4 covalent bonds. I remember a senior colleague asking me this particular question: why is a whole aspect of chemistry devoted to the study of the compounds of one element, and that is carbon? And it's not surprising because carbon has one exceptional ability, and the ability is that a carbon atom can bond with another carbon atom, can bond with another carbon, to form a very long chain that can contain about thousands of carbon atoms. And they can be straight chains, or the chains can be branched. Do not forget that surrounding each carbon atom are what? 4 bonds. This exceptional ability of carbon to bond with one another is known as catenation. And this catenation now led to the discovery of so many compounds of carbon. So many organic compounds running into millions. So there is need to classify these numerous organic compounds into groups, otherwise known as families. Just as we have it in biology, where living things are categorized into five kingdoms: Monera, fungi, protoctista, plants, and animal. And there's still subdivisions again. Oh, that's a digression. Let's come back to chemistry. So these small groups of families in which organic compounds are classified into is known as homologous series. And each member of a homologous series is referred to as homologue. What is homologous series? Homologous series, from the word series means sequence, and homo means same. So we can take it as a sequence of organic compounds that have the same chemical properties and in which successive members differ by CH2 group. And let's take a family to explain that. Let's take the alkene family. The first member of alkene family is methane. The second member is ethane. The third member is propane. Now let's take any two members, successive members, any two successive members. Okay, all right, let's have the first and the second member. We have two carbon atoms in ethane, C2, two carbon atoms in ethane, and one carbon atom in methane. So 2 minus 1, what you have is 1 carbon. Then you have 6 hydrogen atoms in ethane, 4 hydrogen atoms in methane. 6 minus 4, what you're going to have is what? 2. So CH2. Take any two consecutive members, they differ by the CH2 group. Now let's consider the properties of homologous series. The first property of homologous series that we're going to consider is that members of a particular homologous series have the same general molecular formula. Let's consider alkane as a case study. So their general molecular formula is CnH2n plus 2. Let's see when n is 1. Let's see what the first member looks like. So the first member, when n is 1, we have C, n is 1, so we put 1 here. H2, n is 1, that will be 2 times 1 plus 2. And that's going to give us C1 is C, so 2 times 1 is 2 plus 2, that is 4. We have CH4. So what about when n is 2? When n is 2, we are going to have C2, our n is now 2, so we change this to 2, C2, H2 times n is 2, we change this to 2 plus 2. So that's going to give us C2. So 2 times 2, that's 4. 4 plus 2, that's going to give us 6. So you can pause the video and try when n is equals to 3. When n is equals to 3, you are going to have C3H8. Another property is that they have similar chemical behavior. They have similar chemical reactions. Members of a particular homologous series have similar chemical reactions. A very good example to consider is combustion. Generally, members of alkane family can undergo combustion. Let's take the first member as a case study. The first member is methane. Methane plus oxygen. The oxygen has to be in excess to get CO2 and water. So even if it is ethane or propane or butane, so far the oxygen is in excess, we are going to get CO2 and water. Combustion is just a fancy word for burning. If the oxygen is not in excess, then our product is likely going to be carbon dioxide or carbon. Another property of homologous series is that there is a gradual change in the physical properties of members of a homologous series as their molecular mass increases. Let's take the alkene family as a case study. The first member is methane, that's CH4. and the molecular mass is 16. Let's take another member. Let's take octane C8H18 and the molecular mass is 114. Let's consider octadecane C18H38 and the molecular mass of that is 254. So you can see that increase in molecular mass. And methane is a gas, so as the molecular mass increases, there's a gradual change in their physical property. So octane is a liquid and octadecane is a solid. So you can see that change in property from gas to liquid to solid. The first four members of the alkene family are gases. The fifth member to the 17th member, they are liquids, and up above from octadecane above, they are solids. The same thing applies to their melting points and boiling points. It also increases as the molecular masses increases, but solubility decreases as their molecular mass increases. Yes, another property is that they have the same functional group. Functional group will be treated, will be handled, will be considered comprehensively in another video, but I'll talk about it briefly here. Functional group is an atom, it's a group of atom or a bond that is common to a homologous series and it determines their chemical properties. Let's take alkanol as a case study. Alkanol, let's take a member, let's take methanol, the first member, methanol, CH3OH, the second member, ethanol, C2H5OH, another member, propanol, CH3H7OH. So, what's common to all of them? The OH group, OH group, OH group, that's the hydroxyl group, and that's their functional group. It's common to all members of the alkanol family and it determines their chemical reactivity. See you in the next video when we are going to talk about functional group comprehensively. Thank you for watching.